Hello, everybody. Thanks for the introduction. My name is Erik Holtslag, Pondera consult. So we've been invited by Synspective to show a couple of nice use cases in this geo-awesomeness environment. What can we actually do with SAR data in practice, in real life cases? So in the next 20 minutes or so, I'm hopefully going to show you and teach you a little bit more about how the industry uses SAR data and combines that with novel scale modeling. So that's one of the elements that was also addressed in the last question during the previous for the previous speaker, Shanta, is can you actually model future wake effects? Well, actually, Shanta, yes, we can. So I'd gladly like to take over the stick over there. Revolutionizing offshore wind with SAR and LES. LES, I'll explain later. We'll briefly start with an introduction of us, our company, and then move on to the LES model called GRASP, focused on a use case, and then show how SAR has helped in that specific case to reduce uncertainties in the development of the project. The introduction is best done through a short video of what we are and what we deliver as a service to the market, which I'll show you next.
My name is Matthias Haag and I'm one of the directors in Pondera Offshore. I'm working here as the project director for the NNG offshore wind project. NNG is a 450 megawatt offshore wind park and it's built off the Scottish coast about 12 miles off St Andrews. This project is going to be quite an important part and a key milestone for the Scottish energy transition. It's adding 450 megawatt of capacity, which will be enough for 375,000 Scottish homes. It will also avoid 400,000 tons of CO2 per year. NNG is owned by ESB and EDF in a 50-50 joint venture, and they are the two owners of the project. Pondera came in early to the project and helped building up the team, de-risking the project, fulfilling some of the key roles basically in the project. So for example, the project director, the HSE manager, the construction manager, a contract manager, interfaces. We have a lot of people who are really experienced in what they're doing. They have built multiple offshore wind parks, and that's how Pondera adds value to the project. Pondera can advise in all phases of the project. It starts from the very start with finding wind measurements, finding the right sites, helping with consenting, with permitting of the site. But Pondera can also help to arrange for financing for that project and help people to execute the project, so actually building the turbines up offshore as well as onshore. And I think that's the strength of Pondera, that it can actually help throughout all phases of the project.
All right. So hopefully that gave a bit of a view of where Pondera stands, but also specifically what actually is an offshore wind farm. You've seen the massive sizes of those elements, which is quite difficult to judge or to feel when you're normally sitting behind your desk, as most of us, I guess, are on a day-to-day basis. Who is Pondera? Well, you've seen what we deliver sort of in terms of services. We are a renewable energy consultant, so more than just wind. We also do solar, geothermal, battery storage. We are in the market since 2007, currently with around 80 people and massive growth ambitions for the coming couple of years. Our primary office is here in Arnhem in the Netherlands, but we have branch offices in Asia, specifically in Vietnam, Indonesia, South Korea, and one other interesting thing to mention is that we own and operate our own fleet of LiDARs and operate those LiDAR for other parties as well. Most of you are familiar with LiDAR, no doubt. We operate them in a slightly different way than I guess most of you are familiar with, but we'll get to that in a bit. our services for offshore wind, apart from what you've seen in that nice movie just now, we do a lot of works in the preparation phase of offshore wind farms. Specifically, our team, we focus on wind measurements. So determine how basically in the end, how viable a project is on a certain location using floating LiDARs, using onshore LiDARs, using models. And that's where specifically in the last couple of years we focused, is to improve the modeling capacity. And with a rapid increase of calculation power that has become possible, we use a model called GRASP, and that is developed by a Dutch TU Delft spin-off called WIFL. And GRASP is able to solve the atmospheric turbulence processes to a very high level. I'll show you a couple of nice sample movies later. And we deliver specific services for the offshore wind market as well as the onshore wind market based on that model. So what is GRASP? Well, just to give you an example, here for a beautiful sunny summer day in the Netherlands, you see on the left-hand side the true satellite picture of the cloud cover, and in the center what a traditional weather model would make of that. So pretty coarse simulation of that same cloud cover. Now, GRASP, the LES model, large lighting simulations, is able to mimic the atmospheric processes to that extent that it actually is able to locate the same cloud formations quite nicely throughout the Netherlands. So I presume you see my mouse. We have around 30 kilometers inland from the coast a nice cloud formation, probably caused by a sea breeze. And actually you see some nice cloud developments even over particular islands in the southwest of the Netherlands. Those same cloud formations are predicted by GRASP, as well as that same nice sea breeze front 30 kilometers inland. So it shows what the resolution is that GRASP can actually provide to your calculations. So how does it do that? Well, basically GRASP is a very high detail weather model. So we take all sorts of local data of the local circumstances and blend that to come up with a forecast. So for example, it takes the land contours, it determines whether the underground is sea, water, and it takes the temperature of that. It looks on the vegetation, whether there's leaves or not. It looks at the topography of the terrain, whether you have any local speed up effects, and it looks at, for example, is there any specific turbines available? Now, there's other parties in the market that do that, but nobody, no other party does it as detailed as GRASP can, and nobody can tailor it as specifically as is possible in GRASP. And then all of that is being triggered, basically the model is being triggered by ITER5. You've heard that name before. That is being fed into the same model on a 30-kilometer grid, and then basically on a 1 second to 1 second basis, the model mimics the weather patterns based on all the conditions that we've drafted before. So what does that look like? I'm going to show you another movie, see if that works now from the materials. I'll use the slides. Yeah, here you see a nice storm called Polly being simulated that was over the North Sea last year summer. It was a rather extreme situation. Normally summer storms are weaker and rather rare. I would love to see the movie again, if possible. In the meantime, I'll keep on explaining what we were actually looking at. The movie depicted the behavior of the storm. You can actually see it develop, and this is exactly where up to 6 gigawatts of offshore wind is being planned in the North Sea in the coming 6, 7 to 10 years. And in the right-hand side, you see a nice overview of the planned wind farms with the respective wakes behind it. So you can actually see the wind direction rapidly changing throughout the various time steps. So here you can see on a second basis the output of the model. And at first, when I saw this movie, I was a bit surprised. Like, why don't I see any wakes behind any of those wind turbines? Well, actually, the wakes are there, but the wind speeds are so high that the wind turbines have reached their maximum capacity, and so the wakes decrease. So the next one is another nice demo for a slightly lower wind speed situation, and it will run slightly smoother. Not that stormy a few years back. And here you can clearly see for that same group of planned offshore wind farms what the behavior is of wakes behind the wind turbines. So in a sense, we're mimicking the wake effects that you've seen in the previous presentations being captured by SAR. We actually mimic them, and we can actually also forecast the impact on the wave conditions. Now, the beauty here is that you can actually see the wind varying in a rather natural way over the projected wind farms, and you can clearly see that the wind turbines take out a large part of the energy that is in the wind. And so the yellower the wind field is, the higher the wind speeds are. If possible, I'd like to go back to the presentation. So now let's focus on a case study. Here in the Northwestern Europe, offshore wind is becoming sort of an established industry. We know where the winds are. We know that the wind is sufficient to make wind farms financially profitable with or without some government support. The question here is more on, okay, what is the last decimeter per second in the wind speed as we can determine it? For emerging markets, the question is much broader. Where is the wind, and is that wind even closely strong enough to make a profitable business case? And that requires a different approach. So you can't just get away with ancient measurements that we have here, based on oil rigs, based on meteorological stations, based on massive experience that has been built up in the North Sea for the past 30, 40 years. And I think the same goes for the east coast of the US, for example. So you have to use a different approach. We're going to demonstrate how we've looked at some of the possibilities in Indonesia, specifically here around the coast of Aceh. You can see it's a bit of a mountainous island, and specifically that forces the winds to move around the mountains and volcanoes that make up the island ridge. And that's also nicely presented in the Global Wind Atlas. You've seen some slides before where the results of the Global Wind Atlas are depicted. Here, for the same Aceh case, you can clearly see that the wind is being forced partly over the high mountain ridges as well as around it and between the various islands. Now, that's all nice and well, but this is still a model. How do we know for sure that the winds are actually there and that the winds are indeed as attractive as the Global Wind Atlas appears to project? Well, traditionally here in Northwestern Europe, you would say deploy a measurement campaign, either through onshore measurement devices using the long-range scanning LiDAR, or put a buoy in the water, a floating LiDAR, as you see here on the right-hand side of the slide. The LiDAR in this case, and here we're back to where I started, is a ground-based LiDAR, and it measures based on the Doppler effect of light being scattered off air particles, moisture droplets, salt. It measured the wind speed in layers of, let's say, 10 meters all the way up to 300 meters into the atmosphere. And that's a brilliant way to sample the atmospheric boundary and combine that with data measurements of the ocean surface. So the wave height, the currents, the tidal influences. But a campaign is, to start with, super expensive. It is uncertain because it is a rather vulnerable device. You need permits. It's a bit tedious to prepare. And ultimately, it's needed for your business case. But the question obviously is when? When are you going to spend that, give or take, €1 million per year for a campaign? So we have the floating LiDAR. You could place a measurement device at the coast. You could even build, as we've done here in Europe over the past decades, offshore met masts, but they're again a factor 10 more expensive. Or you deploy on the nearest coastal possibility or island a ground-based LiDAR. That does the same thing. It measures up to 300 meters, but only at a fraction of the cost. So here I'm going to show you what GRASP, the LES model that we work with, has mimicked the conditions of the coast of Aceh. We'll keep that one for later. As you can clearly see here, you see the same wake effects around the island. So the speed up effect of the wind over the island ridges. And here we were gonna show the effects on a second-by-second basis for one selected day of how does the wind was being forced through the envelope. So what have we done is we have performed an onshore measurement here with a LiDAR, the land-based LiDAR, and we've compared that with our LES run. So the 1-year run in that high-resolution weather model, and we've compared the output of that model at 100 meters with the onshore measurement. And you can actually see here in the graph on the left-hand side that there is an almost perfect fit. Of course, there is some scatter, which is not strange. There are certain local behaviors that the model is simply not able to capture on a 10-minute to 10-minute basis. Please keep in mind that area 5 is on a 30-kilometer scale and on an hourly basis. So anything in between in the model is basically random atmospheric behavior that could be spot on, but more likely it's not. What is more important is the actual averages. And we see that the average here at 100 meters in this case is almost perfectly on the 1-in-1 line. You may wonder, why don't you have any scales next to this graph? Well, these measurements were performed on a commercial basis, so we have to be a bit careful with not revealing too much of the sensitive information. The same thing goes for the vertical profile. So we've been able to measure with the LiDAR the wind speeds from 40-meter height all the way to 300 and run a GRASP model for that same period. And you actually see that there's an almost perfect fit in the increase in wind with height. So now that's all nice and well. We've demonstrated that at the coastal location, the LiDAR matches very well with our GRASP output product. But we're interested in what is possible offshore. How do we know that offshore it's actually also accurate? Well, in order to do that, we've looked at Sentinel-1 SAR data and possibly in the future other products such as from Synspective could be used for that. We've looked at, okay, how well do the SAR images compare with the same output from GRASP at that same 10-minute period. Bear in mind that, of course, GRASP is being fed on an hourly basis and a 30-kilometer resolution. So we had to look for, okay, what is the similarity in wind patterns, which is not always on a 10-minute to 10-minute basis. But here we have some of the results. You have two graphs consisting of 3 windows. And we start on the upper left one. We have the grasp image for a 10-minute time frame centered around the snapshot basically made by SAR. So you see in the center image the SAR derived wind speeds over the project area that we were investigating here. And what is interesting is that you see the clearly lower wind speeds at the center of the site with higher wind speeds at the western and eastern side. That same pattern is predicted by grasp. So you would say, well, nice, but bear in mind that there's some randomness in the process. So we have actually looked a few slides back and forth within the grasp output to see, okay, what is actually the better match? And we found an even better fit a few time steps later that almost perfectly mimics that same lull in wind speed here at the center with higher wind speeds at the edges. The resulting difference between the two is always presented on the right-hand side, with anything between the orange lines being plus minus 1 meter per second, basically being white. The whiter, the better in this case, because it gives more certainty to your estimation. So I'm going to show another couple of nice slides. Here on another beautiful day in summer 2022, we have run grasp, and you can clearly see the same speed up effect between those two islands being mimicked by grasp and being almost perfectly simulated in SAR as well. You can clearly see the lower wind speeds on the lobes, so south, east, and northwest. That is coming back in the SAR out in the grasp output as well, resulting in effectively an almost perfect match between grasp and SAR. Here we see a slightly less perfect result. We've been digging into why is that possible. Well, this is typically to do with the resolution. We've seen that this lower wind speed is actually in the SAR images. It just sits outside of the domain that we are looking at. And it sits roughly 5 to 10 kilometers east of where we are. So the lower wind speeds are there. They're just not in the domain that we are interested in for this specific site. And by amassing enough of those samples, you actually get a feeling for, okay, how well is your 1 year grasp output that, remember, connected very well with onshore measurements, how accurate is that over your entire project site? So we basically validated the grasp output based on the SAR images. I've shown only 3 images here. The average difference that we found over 13 images for that 1 year that were available is 0.3 meters per second. Now, obviously, this is still sketchy statistics, but it provides a really good impression of, okay, are we looking at the right site for our wind development? The answer in this case I'll have to give you is yes. We are looking at the proper site. We have to be a bit careful with where we plan our future measurement campaign. But we've learned quite a lot of how the local circumstances are influenced by those mountains, which is properly captured by grasp. But obviously the reality is slightly more flexible. So we found the wind speeds to be varying over the site. Last but not least, traditional on-site measurements are expensive, specifically if you develop new sites. In order to get things right, it's smart to run an LES model, large eddy simulations, and by comparing that with SAR data, you're able to reduce your uncertainty and your risks, and therefore, in the end, the cost of a new offshore wind farm being planned. So much for my introduction of how we use SAR data in combination with LES modeling, and please follow the links presented here in case you have keen interest in viewing the movies once again. you.